Good afternoon. You just witnessed me rebuild the entire bottom frame of my CNC project, and I feel like we should talk about it. This was supposed to be a new video, but now it's more of a sequel to the previous one. There were a few features about the earlier version, the one shown in the previous video, that I wasn't too happy about. The alignment of the ball screws and rails became very hard due to poorly machined surfaces. At the time, I only had access to a very old milling machine that was rather inaccurate. I'm also not a great machinist, so the combination of the two wasn't great. Now, having learned from the previous build, and also having access to a better milling machine with proper DRO kind of pushed me towards remaking the frame. I also went ahead and fixed some design flaws while I was at it. For example, having a really wide T-slot table as the working surface is kind of nice, but it wouldn't allow me to face the top surface with the machine itself. I'd planned for this and machined it sort of flat beforehand, but it still bugged me since I knew it wasn't actually flat, nor would it be perfectly aligned at the end. We'll talk more about the flatness in a bit. Anyways, looking at the new model, you can see that the x-axis has kind of been flipped upside down. The long base plate is fitted straight on top of the y-axis sleds, and a shorter 200 by 300mm mounting plate has been fitted on top. On the previous model, the placement of the linear components also wouldn't allow for full movement on the x and y axis. I went ahead and modified the mounting spots for the rails and screws to get the full 200mm on the y direction as well as 300 on the x direction. This model also allows for better placement of the limit switches. Now back to the flatness part I mentioned earlier. As I said, the previous components definitely weren't flat, even though they had been faced with a milling machine. As you saw in the video, after facing all the mounting surfaces, I used a coordinate measuring machine to actually measure the shape and flatness of the milled surfaces. Being a calibrated coordinate measuring machine, it gives results with a sub-micrometer accuracy. What I did was I measured both mounting surfaces for the rails to get an idea about the flatness and parallelism of the two surfaces. Straight out of the mill, the surfaces only had a flatness of around 1/10 of a millimeter. Now what this means is that if you were to draw two parallel planes that best present the high and low point of the actual measured surface, the distance between the planes would in this case be 1/10 of a millimeter. From the form graph, we can see that both planes are actually curved and the measured points are higher in the middle of the plane. This is due to the milling machine having some sag on each end of its x-axis movement. When you drive the table from its minimum to maximum x value, the table will sag for about 1/10 of a millimeter, causing a corresponding error on the machined surfaces. Now while I'm at it, I want to point out that this kind of a measurement is really hard to do with just a dial indicator and would require use of known flat plate to measure the frame against. The traditional method of attaching one of the rails and moving the dial indicator along the other surface only gives you an idea of the relative error between the two surfaces. If both faces are similarly bowed, the dial indicator would read 0 all the way through. In this case, it would have shown just 0.03 of a millimeter in the middle. As we saw, the true error is closer to 1/10 of a millimeter. The linear rails are designed to adapt to the shape of the base they are mounted to. This means that just bolting them down to the frame would have caused a bow of around 1/10 of a millimeter to my y-axis movement. In other words, the error on the milling machine I used to face the surfaces would have been transferred to my machine. What I did was an old-fashioned way of scraping and then grinding the surface down. I did this in a way that I removed more material from the middle and therefore corrected the error. I did the best I could and got the flatness down to a few hundredths of a millimeter, or under 1/1000 of an inch. I also used a coordinate measuring machine to measure the ball screw mounting surfaces to make sure that those are parallel to the rails. Now as you can imagine, the machine itself is quite a bit easier to assemble at this point and will produce way better parts in the future. Also having a smaller work holding table moving around instead of the full 500mm wide one makes it easier to place the machine into some kind of a housing. Great, now as you saw in the video, the y-axis is pretty much done and the x-axis will follow closely with the same new manufacturing methods being applied. Hopefully on the next video we will have a completed mechanical assembly of the bottom frame. Now thank you for joining me on this update video and I hope to see you on the next one. Cheers!